Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today, I have this little boost regulator, this little board. Pretty cool. I think it was like 12, 13 bucks on Amazon. That's quantity one. The amazing thing about this guy, it's kind of funny. They actually offer it in quantities of 2 or even 5 on Amazon. And I think in quantities of 5 it was like, I should have bought 5. It was 15 or 16 bucks or something. I don't know why I didn't notice that the first time around, but I'm gonna have to double check that. But anyway, I'll put a little note here if that's correct. If it is, that's only like 3 bucks a piece or something for these. I thought when I saw it for 12 bucks, I thought, wow, what a deal. 150 watt boost regulator. Okay, so what we're gonna do today, by the way, this came in this little box here, so it's packaged nicely. I'll put a link down below. By the way, that helps me if you buy stuff on the link. Even if you don't, if you buy a frying pan, it helps once you've got an Amazon on my link. Sorry for the commercial. Anyway, so this little cool guy came with these little mounting posts on it. With little nuts on the top. I like it that they're metal instead of plastic, and they're little brass fittings. It looks like maybe, I don't know, 1/4 of an inch high. So it's nice because you place it down without damaging anything. And they didn't put them in a little bag where I had to put them on. They just gave them that way. And also these terminal blocks, by the way, are really nice, quality. Some of these, when I put my big old copper stakes in them, they don't tighten down because they're kind of plastic inside. They just don't tighten. These, I could really cinch them down. So pretty nice heat sinks. So nice construction. Nice size inductor. Nice heat sinks and transistors and capacitors. So not a lot of parts on this board. A little switching chip on this side. Okay. This video is going to be short. I'm just going to power it up, show you what it looks like powering it up. We're going to look at the voltages, and I'm going to show you something at the end of the video that came up that was pretty cool. It's a pretty cool example of how power supplies work, boost converters, and pretty much any kind of converter. So I was using my Instec power supply, my GW, and I found something cool about that, and just by accident the way it worked is kind of pointed out kind of a cool feature of pretty much any switching power supply design should have that feature. So wow, I just leaned against this resistor. I actually just got through doing the test, kind of going backwards on the video, and this thing's toasty hot. Wow, I only had about 50 watts into it, I think, but jeez, that thing's a pretty good sized resistor, and it's nice and hot. This thing's cool. Efficient. Nice. Didn't even calculate the efficiency. So this, I'm going to do I think 2 videos on this. The next one, I might do 3. I'm going to do 2 videos on this. The next one I'm going to show more of a close-up on this and a schematic diagram. We're going to look at a notebook, kind of how to design it. I'm going to do I got a little simulation software. I think I've demonstrated that before on diodes. I'm going to use that to kind of show, because it's pretty cool how it shows how electrons flow. And so we're going to do a few things like that on the theory and how this thing works. And then the next video, because I want to make these short, the next video I will test this guy more thoroughly. We'll look at the ripple. We're going to look at the gate on these FETs. We're going to watch them actually switch on and off, and I'm going to give some troubleshooting tips on how to troubleshoot these bad boys. So I think a little 3 video series instead of 45-minute video, because it seems like that's what they end up being. Let me know what you think of that, if you like that, or if you just want one long video doing everything. So let me know. What do you guys rather see? Okay, let's just power this bad boy up and see it work. Okay. Alright guys, so this is the initial power up. And I got this Tektronix TX3, this cable right here, coming over to the output, and the fluke here, 189. I'll get that out of the way. And that is going to the input, the red and black here. So yeah, blue's going to the red and green's going to the black. And then we have our little power supply here and the 8 ohm load. Alright, and these leads are going off to the power supply. And here's a scope probe. And I'm just using all these little alligator guys right here to kind of hold the wires down so I don't have to take the time to solder them or anything like that. So that's what these guys are here for, is just to hold the load wires onto the resistor. And same with the big old clamps on this side. Okay, and get that out of the way so you can see it. Alright, I'm going to go ahead and bring up the input voltage and you'll be able to see it coming up right here. And here we go. Now, I'm at about 3 volts right now, 4 volts, and you can see the output is tracking it with a drop, like a diode drop to the output. It's actually a synchronous FET, but that's the only thing. Oh, and there's an inductor in the path too, but okay, so bringing up the voltage, and you'll see the output voltage jump when the switcher starts going. Right now the voltage is just passing through. 9.5, 10 volts, and just over 10 volts it jumped up. Now with the load, I'm dropping a little bit of voltage now at the input. The input dropped down to 9 volts now. Bringing up the input voltage now. So I'll explain something here in a minute. You saw my input voltage just jump way up. That's because my power supply isn't actually capable of putting out enough current at that low voltage. So that's why the voltage dropped, because it kind of folded back. And then once I crept the voltage up high enough, then it could sustain that current. So that's why it jumped up, and then I had to bring it back down. So that's not ideal. That is not ideal. Alright, well, so you can see 21 volts at the output. I don't really feel any temperature here. Caps are nice and barely getting warmer than room temperature. Everything feels pretty cool at this temperature, at this power level. Okay, so the input power is 12 volts at 2.54 amps. The output is 21.26. So we can adjust that screw there and adjust it to the voltage we would want. Let's say we wanted 19 volts. We can adjust this down to and if you're looking at that meter over there, it's 18.9, 18. This is a nice Bourne's pot multi-turn, so it's easy to adjust to get a fairly precise measurement, as you can see. I mean, it's probably a 10-turn pot at least. So yeah, you can adjust that fairly precise. Now if I want okay, so by the way, if I wanted 19 volts, I'd probably, if anything, error on the high side just a little bit, unless there's reason not to. So I would go a little bit above that, maybe even 19.1, so that way it account for some voltage drop across the leads, because I'm measuring the voltage right here at the terminal blocks. That's where you want to do it. If you had some leads, a cable for instance, that you knew that you were going to power something, you'd want to measure that voltage right at the end of that cable with it loaded down, so you could take account the voltage drop of the cables. Okay, So yeah, there's the initial power up. Everything, the caps, I like to fill these aluminum electrolytes to make sure they don't get hot, because if they haven't chose good caps, they'll get too hot. But nothing right now is getting, I mean, it's just above the room temperature. That coil, which is a nice size, it feels very cool. The caps are actually about the warmest thing. The heat sinks, yeah, the caps and the heat sink, yeah, similar temp probably. Alright, so you can see the little IR meter here, and you can see the, oops, sorry, you can see the capacitors here. They look pretty cool. The inductor looks actually the warmest thing, even though it felt cool to me. It says it's 45 degrees now, so if you can see that jumping around right there. I'm going to go back down and fill it. Wow. I guess, I mean, that's what the meter is saying. Now, here, let me zoom in on this so you can see it. Up here it shows the temperature of the center of the screen. So if I put the center on that core, it says about 45 C. And there's a little hot one, a hot point that jumps around, moves, but the center point is so I can aim, and it tells me here. And then there's also the cold one, if you see this green one jumping around. So it's 22 degrees ambient in here, if you see that right there. It's about 40, here I'll put the center of it on the hot spot again. And about 45 degrees on the hot spot. So it's about a 22 degree rise, 22 degrees Celsius. Huh, interesting. Now one thing I can say is the top of those capacitors, if you put a little black electrician's tape when you use these meters, it'll work better. Because right now, if you notice, the center is blue, which it's not. If you notice, the outside's kind of green, a little hotter, and at the top it says it's the coolest. That's not true. That is because it's reflective. That shiny silver is reflective. So you need to put a little black electrician's tape. Well, pretty much any kind of tape would actually work, but you just don't want a shiny metal surface if you're trying to get accurate readings. Well, there's a emittivity setting on this, which emittivity setting on this thing that helps set that reflective thing. It's best just to put some tape on it though. Alright, so that's initial power up, and just kind of showing you the temperature, just kind of initial look-see. I don't know if I pointed out the red LED or if you could see it over there, but there's a little red LED there. So there's a little red LED popping up. There's the input terminals up there and the output terminals here. And this is our input capacitor and our output capacitor. Alright, well, there's our initial power up. And the setup of the power supply, right now I don't have them in parallel, which I should have done, because when I turn up the voltage, it only puts out 3 amps on one side, and it kind of had a problem. So I meant to plug this in a parallel mode, and I did not do that. So it was independent, even though the meter thought it was in parallel. That was kind of a mistake I made. I forgot to hook this up. So the meter tried to put out more current, couldn't do it. So sorry about that, but for initial power up, I think that's okay. So independent, I should have had these both out. You can see the lights, it was in current limit. So when I first powered it up, it didn't like it too much. It's interesting when I do this, it changes the voltage, but hold on. You know, I think I just learned something about this power supply I didn't know. I actually was in, you notice that? I can turn the voltage up, nothing happens. So I'm in independent with both buttons out. So I thought I had to hook this up in this way to put them in parallel. I think it does it internally. If you hear the clicking, oh my heck, I didn't know that. Listen to this. I'll push them both in for parallel. You can hear the relay click inside. And then the, oh, so, okay, my bad. Wow, you learn something every day. This is a pretty new power supply for me. GW Instec. Really nice power supplies. By the way, they make this Tektronix power supply. I had confirmation on that. This Tektronix PS2521. Here, I'll zoom out so you can see a little bit better. Whoops. My little Tektronix down here. Yeah, Instec makes that. Or made it. I don't know if they're still being made. Okay, so anyway, yeah, wow, that's cool. I don't have to use jumpers to put them in parallel mode, so wow. Jeez, that's really cool. I thought you had to use jumpers, and I thought that this was master and slave and that you just got to control this, but I guess you don't even have to worry about any of this stuff. It just automatically does it for you. Pretty darn neat. Alright, well anyway, so I set this up. I just cranked the current up maximum, and then I brought the voltage up this way. And so it puts out a maximum of 6 amps, okay? But at the low input voltage of the boost regulator, it pulled a little bit more current, so the voltage folded back until I got the voltage up high enough, and then it was able to kick out the extra current, or the extra power. Well, actually it didn't need to put out so much current, right? Because less voltage. So, alright, something I should explain, I think, is that when you, if you need to put out, say 20 watts, if your power supply is at 10 volts, it's going to put out 2 amps. That seems obvious. And if you're 20 volts, it's going to put out 1 amp. We're powering up a switching power supply over here that's going to regulate the output. So it's going to make, and I have an 8 ohm load on the output. So it's going to maintain that load regardless of the input voltage as long as I'm within the range. So if I'm in low range, it's going to pull more current. If I'm in the high range, it's going to pull less. So that's why when I cranked up the voltage, then the current dropped down, and then when I did that, all of a sudden the voltage just, you know, swung way over, which that's not ideal. So, you know, but anyway, that's what you saw when I was powering up the meter. If you go back and look at that, if you didn't notice that, and then as I cranked it, you know, then I had to bring the voltage back down to 12 volts where I wanted it. In a power supply design, if this was going to be your input power and your switcher, you did not want that to happen, then they call it under voltage lockout. You don't let it turn on until you have enough input voltage that you can handle the current. So maybe where this guy was turning on, this boost regulator is turning on at 10 volts, maybe we change that to 11 volts. So it's a little bit higher, so it doesn't draw so much current. So anyway, okay, there's a little lab power supply explanation, which I'll tell you what, there's many times in a lab where people will say, oh, your power supply is not working, and that's because they didn't have the current limit on their lab supply high enough. Because when it first starts up, there's going to be an inrush of current, and if the voltage is low, it's going to draw more current than what they expect, and this guy will actually shut down the power supply they're testing, and they'll think that it's your power supply on the bench when it's really the lab supply. Just kind of a heads up there. Now, I want to just show you this. I'm going to power it up, okay, so now you can see what it looks like on this end, okay? Let me turn the lights away so you can see that display a little bit better. Okay, now let's go ahead and bring it up. Now, when I'm powering up a power supply, what I like to do is I like to look at the current and the voltage. Now remember, this current is actually doubled because it's, see if I put them both to the current, I got 0.3 here and 0.25 here. This side's putting out just a little bit more. So if I take this up to say 7 volts, see they're pretty close, but each side of this power supply is sharing the current. So roughly it's twice this side. So I put one side on current and I put one side on volts. So that way I can tell. Now the volts are the same on both sides because they're parallel. Okay, now watch what happens. When I bring up a power supply, what I like to do is watch this current, make sure it's not too high. Now in a boost, it's a little bit different because I'm going into an 8 ohm load, and so basically I have 8 volts at my load right now. Okay, so I'm going into 8 ohm load, so I'm pulling about 1 amp. So if I go here 0.52, 0.48, that's 1 amp, right? So now it's 8.5 here, but it's, we have a half a volt drop to the power supply, so it's 8 volts at the load. Okay, remember that when we saw powering up? Okay, now I'll bring this up. Now on a boost, the current's just going straight through until the switch starts boosting. It's just going straight through. Now right about there is when you see that current jump up right at 10 volts, and see I'm in current limit here. Okay, I'll bring it down. Now another thing, you notice the power supply, it's still 15 volts on the output. It's still boosting, so I'm still drawing a lot of current, and I'm below 10 volts. Why is that happening? Okay, notice that, oh, it just dropped out, so I had to go down to 8.6. all right, let's do now. Well, here, let me just explain that. It turned on at 10, right? Watch, it'll turn on at 10. Watch, it takes a big jump just over 10. What? Wait for it. There it goes. And then look, now my voltage folded back. Well, it doesn't turn off until I get down past 8 volts, or I mean down lower, right? Close to 8 volts. Let's drop it. Right there, 8.5. So, the boost regulator design is set up exactly to protect against problems like with power supplies like this. When I bring it up to 10 volts, just over 10, the amperage jumps up quite a bit. Right about here, right there, and then the voltage drops back down. It folds back. It's kind of current limiting, so it's folding my voltage back. Okay, but I didn't turn off, even though I dropped below 10. And the reason why, it's called hysteresis. The voltage has to drop down so much before it turns off. That's to keep you from, if you're right there at the point where it turns on, it would sit there and chatter, on off, on off, on off, and it'd sit there and chatter, and it'd draw a lot of current, stop, draw a lot of current, stop, and it'd go nuts, and it'd cause lots of noise, and some, sometimes it damages the power supply. So they have a hysteresis in there where it'll turn on, and it won't turn off until maybe 1 or 2 volts below. So it allows the voltage to drop a little bit without turning itself off. Okay, so that was actually kind of cool that we were able to demonstrate that with this power supply. I mean, by accident, actually. Okay, now I'm going to creep it up. Now you notice nothing's changing because my red lights are on. Okay, so I'm going to change. Oh, see, it just turned off. So now all of a sudden, control, but boom, the voltage just, once it came out of current limit, it just jumped way past what I wanted. I wanted 12. But let's say if I was on a battery, that's okay, because you expect 14 volts. Actually, 14.3 probably. So that actually would, and this power supply input, this boost will take more, more voltage than that without being damaged. But if you were, okay, so there's about 12 volts right there, okay, and 2 amps, so that's about 24 watts. But that's because I'm ignoring this one. So they're almost the same. So really we got 4 amps from each side. So it's really twice that. It's 48 watts. So we have 48 watts on this power supply, and we took temperature readings. It runs pretty cool. Hey, that turned out to be a cool demonstration of a power supply and the interaction and how they're designed to work. So that was cool that we saw that. Hey, if you like this video, give me a thumbs up, all right? Thanks, guys.